Okay, let's see what y'all are up to. 3.6 is kind of the first fun application of derivatives. We just got through with 3.1 all the way through 3.5, and the application of the derivative was that it lent us information about the graph of f, how we could sketch it, you know, if it's increasing, decreasing, if it's concave up or concave down. We could also apply that then to motion, you know, where the position is increasing, decreasing, and then the acceleration would be the second derivative. So just while I'm saying it, remember that the second derivative of a function tells you two things. It tells you the curvature of the original function f, but it also tells you if the previous derivative f prime is increasing or decreasing. Okay, well, optimization is essentially word problems, right? And all we have to do is use our skills that we've already learned to answer more meaningful type questions. In this section, we're going to be essentially looking for absolute extrema. Absolute extrema. Now, we've had a theorem that dealt with absolute extrema. That means absolute max, absolute min, global max, global min, and of course, just max min. If we don't say it, we imply absolute. What theorem was that? That dealt with extrema, extreme y values. Yeah, the extreme value theorem, the EVT. Remember it said, if a function is continuous on a what interval? Closed interval, then there's guaranteed to be both a max and a min on that closed interval. And those max or mins can either occur at an endpoint or at a, where? On the interior at some x value we call a critical value. Right, good. So that's all we're going to be doing in this section. But here's the thing. We don't always have closed intervals. So we looked at the end of that section in 3.1, I believe, on how we could do it without intervals. We might have to learn to justify whether something's a max or min without the EVT to help us. If it's a closed interval and it's continuous, the EVT will help us justify. But if not, we'll have to justify some other way. All right, so optimization is a word that y'all have heard before, right? If something is running at its optimal level, what does that mean? The best, right? It's the best. It's the superlative case in your English class, right? You have big, bigger, and biggest. Optimization is the superlative case. So whenever you want to make something the biggest, the smallest, the cheapest, the strongest, the ugliest, etc., that is going to be optimization. Now, when you do say optimization, what keeps you from, if something is already at its optimal level, what's keeping you from making it even better? Why can't you just keep going? Because there's what? There's usually something that's preventing you from making it better. We call that, in general, a constraint, right? So optimal kind of implies getting the most out of something based on the current system or under the conditions in which we have to work, right? We want to run at an optimal level. So there's usually going to be a constraint factor that keeps you from making it infinitely large or infinitely small, right? Okay, so that's what this question that I threw to y'all was. What the ancient Greeks used to do for recreation before social media, okay, before they had phones. They actually talked to each other, and they challenged each other to these types of games in the street, right, with their togas, okay? So here's the task. Find two positive numbers, and when I say positive numbers, it could be real numbers, so that they add up to 60, their sum is 60, but such that the product of one of those numbers times the square of the other is a maximum, as big as possible. I want to find two numbers that add up to 60, positive numbers, that when I add them up, I get 60 every time, but when I multiply one times the other one squared, I want that product to be the biggest possible it could be. Well, if you have no strategy, what might you do? You might just start picking, right? Let's let one number be A and let the other number be B, okay? If I choose A to be 1, what does B have to be? 59. So let's go ahead and do the product, okay? If you want that product to be big, which one would you want to end up squaring? It doesn't tell us which one we have to square. I would square the 59, so that's 1 times 59 squared. Okay, and then we could see what that is. And we could say, oh, that's a big number, but I wonder if there are other numbers out there that are bigger. Right? What about 3 and 57? That would be 3 times 57 squared. And if we keep going like that all the way to, I don't know, 58, and then this other one would have to be 2, that would be 58 times 2 squared, so on and so forth. Is it necessarily true that the biggest product is going to be 1 times 59 squared, or is there some other number in between? And we're only considering integers here on column A and B. They could be any real number. This is not a very tried and true method. Just because in your list you found a product that is bigger than all the others, does that mean that that's the biggest one in existence? No, because we're talking about real numbers. Now, if we were talking about positive integers, that's a finite list, right? 1, 2, 3, 4, 5, all the way up. You can keep doing that and then pick the biggest one. But we're talking about real numbers. So there's infinitely many that we haven't tried, even if we have a list of infinitely many. So we need a more systematic approach, okay? And that's where calculus comes in. Calculus does a great job of routinely and systematically helping us find these maximum and minimum. So let's go ahead and do this. Let's go ahead and say we want to, first of all, let's start with the quantity to optimize. I'll give you a flow chart here. Now, optimize, you're going to know that it's optimized because it's going to say two words. It's either going to be a maximum or a minimum. Okay? The biggest, the largest, the ugliest, the smallest would be a minimum, right? The cutest, whatever. Anytime you see the superlative case, or the most beneficial or something like that, that's also superlative. So what is it that we're trying to maximize or minimize here? The product. It says the product of one times the other. So what do you want to call the product? I called it P over here, or product P. Let's call it P, okay? Let's let the product of the two numbers be P. P for product. I used A and B over here. Let's just keep it going. A times B squared. It doesn't matter which variable we square. You can call it B times A squared. That's fine. So B is the one that we're going to end up squaring. That's what it says right there. All right, now, I want to maximize that equation. But what's the problem with trying to maximize that equation? We have 3 variables. And normally I have to have like y equals something in terms of x. I need to have 2 variables. So I have exactly 1 variable too many. Ruh-roh. So my next task is to try to get that function of P either in terms of A or P in terms of B. That's my goal. Well, that's going to require me to relate A to B somehow. Guess how we're going to relate those 2 values? We're going to find what I call the constraint equation, okay, or your limiting factor. What's preventing us from making A 5 billion and B 5 gazillion jillion? It said they have to add to 60. And those numbers, a billion plus a cajillion, zillion, whatever I said, that's a little larger than 60. So here's our constraint equation. Our constraint equation is that A plus B has to equal 60. And of course, A and B are positive real numbers. Okay, so B can't be 61 because then A would have to be what? Negative. Right. Okay. That's your constraint equation. Now notice, I can solve that equation for any variable I want. It's just as easy to solve for A. It's just as easy to solve for B. But look at what we're going to do. I'm going to use that to plug back into the first one so that I have an equation in terms of 1 variable. When I plug back into that first equation, is it easier to plug in for A or B? Probably easier to plug into A because then I won't have to square it. So think about what you're doing here. We'll solve for A. Not that it matters. It just might make things easier. Now, I like to box that one there once you solve for A because you might come back to that. We might come back to that. I'll put this. Okay, now step 3, you're going to plug your constraint equation into your primary equation, which is the one that we can say for number 1. All right, so we get the product of those 2 numbers is going to be A, which is 60 minus B times B squared. And now we have an equation in terms of one variable. Great. Now here's the thing that's kind of cool. If you were to expand that out, you would have a cubic polynomial, right? It would be negative b cubed plus 60b squared. What's the domain of any polynomial? All real numbers. Whenever we have a mathematical model that's applied to a specific circumstance, the domain may not be the same as the model that's representing it. So we have to find what's called a relevant domain. Find a relevant domain. Okay? And this is how we can get our closed interval possibly. What values of now our independent variable b make sense? Is there a smallest b can be? 0. And is there a largest b can be? 60. Right. Now, here's the deal. It says that I had to have positive numbers. Is 0 a positive number? No. So it can't actually equal 0. It has to be bigger than 0, like 0.0001. Then b can b actually equal 60 then? No, because if b is 60, then a has to be 0, which is not positive. So notice I do have a relevant domain, but it's not a closed interval. Ay caramba. So what does that mean? That means I have a polynomial which is continuous everywhere, but it's not on a closed interval. So if someone asked me how I came up with my numbers and they said, prove it, I wouldn't be able to justify it using the EVT. If I did have a closed interval, then I can just find the values at the endpoints and at any critical value and say by the EVT, that's the max and that's the min. But let's not worry about that too much right now. I just want you to find the relevant domain. Okay, so once you find the relevant domain, it's just part of 3, really. It's like 3b. You want to find your critical values. Find the critical values of your new equation. So I'm going to need the derivative of that. Do you want to use the product rule or do you just want to distribute it? Let's distribute it. So you can put p of b if you want. It is a function of b, p of b, which of course naturally makes you think of lead. Really? Why? 60b squared minus b cubed, right? So that's a nice little polynomial. But we're only from 0 to 60. So let's go ahead and find the derivative. P prime of b is 120b minus 3b squared. And of course, that's never undefined. By the way, for most of these realistic problems, the values that make the derivative undefined are physically impossible. So we kind of ignore those. They are the exceptional things, like vertical tangents. We can't, if we're talking about speed, that would be something going infinitely miles per hour. It's physically impossible. So we're kind of interested in the nice horizontal tangent one. So we'll set it equal to 0. If we factor out a b, we're left with 120 minus 3b. And if we set them each equal to 0, we get b equals 0, or b equals 120 divided by 3, which is what? 40. Now, we got two answers. The cubic polynomial has 2 horizontal tangents. We want to make sure, though, that we're finding values that only fall in our relevant domain. Yeah? Oh, yeah, you could factor out the 3. Yeah, I could have, should have, maybe, would have. Yeah, that's fine. Yeah, totally. That would just make the math a little bit easier. Good point. Sorry, I was focusing on the letters. So do both solutions make sense in our relevant domain? Just one, yeah. So you kind of get rid of that one. And it's in the domain of the function, but it's not in the relevant domain of the application. And so here's the deal. We can't use the EVT, but b equals 40 is probably going to be your answer. Okay, 99 times out of 100, if you only get one answer that shows up and it falls within your relevant domain, it's going to be your answer. Okay, but here's the thing. 40 might be the value that doesn't give me an absolute max, but rather an absolute min. And I would hate to put forth the exact opposite answer of what I was being asked to do. So here's kind of the most fun part. The most fun part, you'll believe that, of any optimization question. Justifying. Oh, boy. You're not always going to be asked to justify. Okay? But when the EVT fails, because we don't have a closed interval, how do we show that 40 is the value that actually maximizes the profit and not minimizes it? Plug in any other value? Okay. If you compare it to any other value and it gives you something bigger, then that would be the minimum. But if you plug in any other value B and it gives you something smaller, that one should be the maximum. I kind of like that idea. Yeah. But what if our function actually looks like this? And I just found a horizontal tangent that was neither a max nor a min. It depends now if I pick to the left or to the right of 40, it may be bigger or smaller. Ooh, that's also an option. So here's what we're going to do. Here's what we're going to do. Let's look at let me go ahead and come down here. Let's factor out the 3. We get 3b times, that's going to be 40 minus b. Okay, so if you were to graph p prime, let's graph p prime. We want to graph it from 0 to 60. Okay, it has x-intercepts at 0 and at 40. Correct? That's what we found. Okay, cool. P prime is going to graph like a parabola that opens what? Down. So it's going to look like this and like that, and then it's going to continue going down all the way down here. Okay, and we'll stop right there, and maybe this point over here should actually be open if we want to be accurate. So what have I done, really? I've just graphed P prime on my relevant domain. Would you agree? Okay, now if I look at what I've been doing, my local max or min, I would say, okay, if I look immediately to the left of 40, P prime is positive. But if I look immediately to the right of 40, P prime is negative. And therefore, by the first derivative test, since P prime changes from positive to negative at 40, the function P has a local maximum at x equals 40, right? But that's a local argument. And we're trying to find not local maximums, but what? Absolute maximums. Now, if you don't have endpoints, you can't use the EVT. So here's what we're going to do. And this is going to be pretty common. Notice, whoa, hang on. Let me get my highlighter down a little bit. Notice that everywhere to the left of 40 on our relevant domain, P prime is what? Positive. Now that's important because if I continue that parabola going to the left of my relevant domain, now it's negative again. But everywhere on my relevant domain to the left of 40, P prime is positive. And everywhere to the right of 40 on my relevant domain, P prime is negative. Everywhere to the left and everywhere to the right. That kind of is more than a local argument, right? Like if I say everywhere to the north of New Braunfels and everywhere to the south of New Braunfels, that's everywhere, right, on the globe, on my relevant domain. I can change my local argument into a global argument. So for now, all the values that make sense, my P values are increasing all the way up everywhere up to 40 and then decreasing everywhere to the right of 40. Therefore, 40 is not just the value where the local max occurs, but where the what? Absolute max occurs. Let's write that down. It's a slightly different wording. So since P prime, you don't say changes from positive to negative at B equals 40. You say since P prime is greater than 0 for all B, and then you can list it as an interval from 0 to 40, that's your relevant interval, and P prime is less than 0 for all B on the interval from 40 to 60, comma, P is maximized, and if you want, you can add a little word here, is maximized absolutely or globally, but remember, you don't have to say that, at B equals 40. There you go. So really, all we're doing is we're talking about a sign change in the derivative again from positive to negative. But what in my argument makes it a global argument and not a local argument? There's kind of two answers. First of all, what does the cap size A mean? For all. That's a very important part of it, right? For all. And then the other important part is I'm addressing not just immediately to the left of 40 and immediately to the right of 40, but my interval includes all the values everywhere to the left of 40 and everywhere to the right of 40 on my relevant domain. Okay, so we're not always going to have to justify. Okay, so I just want to introduce that to you now because that seems to be the biggest burden that students get into. When you don't have endpoints, you can't use the EVT. You have to justify like this. But as I already mentioned, if you don't have to justify, 99 times out of 100, the single value that you get in your relevant domain is going to be the one you're looking for. Okay? So you can kind of just go with it for the most part. All right, so now that we're confident that 40 is not only a critical value, it's the value that's going to absolutely maximize the product, now we answer the question, and that's step 5. Okay? Step 5 is to answer the question. And that seems kind of silly, but there are all types of things that can be asked that are associated with that value, right? Did they ask for the smaller of the two numbers? Did they ask for the larger of the two numbers? Did they actually ask for the largest product that they were trying to get? Did they ask for the sum of the two numbers? Okay? What did they actually ask us? Find the two positive numbers. Okay. So, we'll answer our question. So, the two numbers are, now, should I just list one of them as 40, or does it matter that we're calling it B? Very, very good. Since I've called it A and B, I need to keep my labels on them when I list the numbers because it matters which one we square. And if I just threw out two numbers, 40 and 20, the person who's trying to interpret my results wouldn't know which one to square because they're not smart enough to realize you square the larger one to get a maximum product. So leave your labels. So the two numbers are B equals 40 and A equals, well, gee, how do we find A? You remember back up here I said when you solve that constraint for the other variable to box it because you are going to possibly come back to it? There it is. Right? Now, this one's easy. If you know they had to add it to 60, one's 40, the other has to be what? 20. Pretty easy. But it's not always that intuitive. So you would plug it back into this, and you get A is 60 minus the B value that we found was 40, and so you get A is 20, and A equals 20. Make sure you answer the question. If it had asked for the product, you would then say, so the maximum product is, and you could either find both numbers and plug it back in here, but would you even have to find A if it asked you for the largest product? No, because this right here, you might want to box it, gives you the product in terms of that one variable B. Now notice 60 minus B is right there, but again, it's not always going to be that intuitive. So when you find your optimal value of B, there's usually two things to plug back into. Usually two, sometimes more that you can plug back into. You want to find the other value, plug it into the top. You want to find the product, plug it into the bottom one. Okay? That's why you need to answer the question. All right, so did anybody on your own intuitively in the warm-up come up with 20 and 40? You did? You actually did. How did you come up with 20 and 40? Did you do this? You just guessed. You tried a bunch of numbers and then 20 and 40 gave you the largest product? Oh, you kind of split it? $32,000? Is that it? The largest product? So the largest product is $32,000, which is bigger than 59 squared, I guess, right? I hope it is. Yeah. It would be like 30. Yeah. Okay. I hope it's bigger because otherwise calculus just broke. It didn't work. You'd be like, oh, that was interesting, but why? Okay, I'm going to English. Right? Cool. So there is your taste of optimization. Those techniques that we just did, minus the justifying, because we're not always going to have to do that, that's what optimization is about. So it is just finding absolute max and mins, but guess what? We have to squeeze our own juice. It's like we're handed oranges and we need orange juice. We have to squeeze our own juice. And that's the best orange juice anyway, right? We have to write our own equations. And that's why people whine when it comes to word problems. Oh, we got to squeeze our own juice. Will you squeeze it for me? No, because then you'll never learn to make your own juice. You'll die of orange juice thirst, staring at oranges. Have a great lunch.